I'm Dimitar Pashov from King's College. I'm one of the developers of many body perturbation theory code called Questor, and I did some work trying to port a big part of it, really the jewel in the crown, the quasi-particle self-consistent GW to GPUs a couple years back. Here I'll talk about my experience and lessons from it. So I'll show you some application context considerations. I went through choices made, prep work, details about the usage, and build the lessons and see how it all panned out. So the package is really a large suite going back many decades. Started development some time in the 80s, I guess, or even probably earlier in the Max Planck Institute in Stuttgart. Ole Anderson and many other codes actually can trace their roots there, the other ones. The main components I'm going to mention today are the QSGW, on top here, the highlighted the full potential DFT code and the beta operator solver. It's a multi-theory sort of code, so you can start with DFT, try to add various corrections, global low order diagrams for the GW and the BSC, and can also have a local very high order diagrams to embed it with DMFT. You can have various solvers for that, continuous time Monte Carlo, for example, or the exact diagonalization from Cedric Weber is also embedded in the code. The QSGW is slightly different than the usual entity of what's usually referred to GW. Usually when people say GW, it means the G0, W0. And it's a one-shot, basically one step beyond the DFT. The way it's used, generally people try to pick the best functional they can get for DFT and do one step with that and see what happens. In our case, we are trying to go a bit further. I'll maybe talk about it in the next slide. General use cases are for semiconductors, metals, unconventional superconductors, understanding the mechanisms driving the superconductivity and estimating the critical temperature, materials used in photovoltaics as well, and so on. So let's move on. Basis set is one unique feature of the code. It's no electron atom-centered augmented basis. Augmented meaning that within some region around an atom, the basis is numerical and is obtained by solving the local Schrodinger equation, while outside of that is linked to smooth functions. The representation here is more complex. It's somewhat similar to the projector augmented wave, and in that the smooth basis covers the whole space and then is subtracted out and represented locally and so on. It's quite minimal, reasonably complete. Usually 2 functions per electron is quite good. And the way it's constructed, it's already fairly close to a solution to the Schrodinger equation, so fairly few functions need to make it good, complete. It is short-ranged, but unfortunately we are not yet taking advantage of it. So method I'm going to talk is not a linear scaling. The PAW representation helps take advantage of low expansion cutoffs in comparison to FPL, APW, and things like that, which people might be familiar with. And here's a few pictures of what it looks like. For first is S function, second is a P function, and third is one of the D functions. And the little odd items around these are basically when a function enters the space of a neighboring atom. So it preserves a 0 value around any other atom. Right, the quasi-particle self-consistent GW approximation. It's a trick to construct a starting point independent ab initio, really truly ab initio rather than parameterized functional. It starts as from DFT, we have some initial starting density as usual. We cycle through, obtain the polarizability. From that, with the Coulomb potential, obtain the screen Coulomb potential W. From then, the self-energy. Then the self-energy is dynamical, is dependent on the frequency. It's getting quasi-particleized, and from that, the starting exchange correlation function is subtracted out. Then, as the cycle goes, usually in about 10 to 20 iterations, you'd have a solution, which doesn't really depend on exactly what function you start from. All right, the present algorithm, as I mentioned, does scale badly. It's a 4th power. There are ways to go lower scaling. We haven't yet gone there, but we have plans and funding to explore that. What I'm going to talk about now is that 4-power scaling code. So that pretty much excludes going for very large systems, because even if they're done in the best possible way, they're just never going to be good enough computing for that, just be a waste of resources. So larger systems are mostly excluded here from the considerations. Small cells are already fairly quick on CPUs, don't really justify going for GPUs, but they can be made to run very fast on GPUs as well. So the main target for the porting is trying to optimize moderate-sized systems, which can, very quickly become very difficult, very time-consuming. For example, before the war began, it was fairly usual for people to run multi-day simulations and to wait for things. Well, now things are completely different. And with usual job time limits on large HPC clusters, it's just a massive pain to have to restart things all the time and so on. So trying to fit in that use mode. First, preparatory work on CPUs. In my view, that's a very important step before touching any GPUs. Of course, one can easily just profile and find some hotspot, optimize it, be done with it. But I think a lot more can actually be gained by looking more carefully at the code. And very often, in my experience, old codes have that misfeature, I guess. They were oftentimes developed in times where memory was much, much more expensive. So algorithms were used which were constrained by this, and they can be really suboptimal for present-day architectures where memory is plentiful and vectorization is basically mandatory in order to get good performance. Well, in the older days, it might be strictly serial and so on. Also agree with the previous speaker about really having to look carefully whether you can represent something with already pre-existing solutions, especially big one is matrix multiplication, 100% on that with him. Many cases I've seen where people are reinventing matrix multiplications within code, merged with some other things and whatnot. Once all that is split out and cleared out, and one, you can cut out huge amounts of code, which is just good. The less code, the cleaner the program is, the easier to understand it is. And the other, by using a vendor optimized library, you gain tremendous amount of speed up without really moving much. You get also free multi-threading and so on. So reformulate to reduce data access overheads. That's another one. Oftentimes, there can be multiple ways to do the same mathematical expression, and thinking exactly of polarizability calculation here, it can be written in a way to reduce data trans accesses, and this can help tremendously. It's the usual complexity estimates that people just don't often include data accesses. Again, in the older days, because it was just assumed that they will be all the same, but with very large caches and so on, things change significantly. So if things can be fitted into cache or into some other fast memory, it can be much faster than having to all the time do global accesses. Once we get to a point where a program can work efficiently, well, with single MPI process per node or with a single MPI per socket, then that's a good point to start looking at the GPU porting. Another perfect way to ruin a good performance is by having unnecessary writing of data to disk and then reading and so on. So a good chunk of the work here was dedicated to redesigning the workflow in the code so that actually two separate codes are merged together and they pass a reference to the data already pre-existing in memory as the screened column potential here. This thing depends on 4 indices and 2 of them are rather large. The first two the mixed product buses. So in a bad world, this would be square of the numbers of states chosen, but can be reduced by down to 1/3 of that, or still this could be many thousands. So overall, that screen column potential could easily be in terabytes. Avoid writing that, even if it's written in the best way with independent process parallelism and whatnot, it's just never going to be good. General GPU obstacles that need to be considered before doing much is the target size data that we handle usually cannot all reside in a GPU memory. The code started development, the GPU port of the code started development in the time where the V100s and before what was the P100s were popular. And these did have quite a bit of memory, but it wasn't really enough to fit everything, even for a moderate size small system. So it has to be a scheme where data is sent back and forth, computing is done asynchronously. That's a juggling of data and overlapping the transfers. I mentioned here using the asynchronous copy and computing. GPUs also are not great with matrices of smaller sizes under 1,000. Okay, the recent hardware editions to 800 is not that bad actually, but still you're not going to get the peak performance with that kind of matrices. So in that juggling of data and computing overlapping, it does help, and reducing the resources allocated to any particular operation so that more of them can fit simultaneously using streams and whatnot is a good idea. The code was done with CUDA, and why that? Many considerations really. As I mentioned, it is an ancient code. It does have very many old features in many places. It's a massive challenge to clear up everything. We don't really have that many resources to do that. It also has, curiously enough, many very new Fortran features, which are not supported even now by NV Fortran. And it just wasn't able to compile it, far from it even at the time. Now it's very close. It's only maybe 1 or 2 features missing that would be doing it. So that first point would be revised, but at the time it wasn't the case. OpenACC, why not? Because again, unless you have the NV compiler running properly, it's not really a good option. GCC only really supports it recently and barely any support at the time. OpenMP, similar story, except that it's always a step behind OpenACC. Other solutions, RockHem, HIP, again, sort of a clone of CUDA, but following behind a specific for AMD. Cocos, more general, but it kind of binds into all that other huge frameworks, Trillanos and whatnot from these labs in the States. I would like to actually go back and look into that again, but at the time, I didn't feel like it could be the risk could be justified. SQL is one interesting option, which again was a bit suspicious at the time. Now probably better idea. Again, lack of experience and low resources didn't really allow too high risk to be taken with these portable options. Another thing is that if the code is designed well and things are abstracted properly and the low-level functionality is really moved out from physical concerns, then the real CUDA code that needs to be written, and I mean the code that device global functions annotated that's running on the GPU, is really minimal in our case. it mostly concerns very simple operations which are simply not available in standard libraries, but might be a good idea to be added if there is more other interest. And there's maybe even things which overlap with some of the libraries developed in the CSCS about sparsity and so on, but on local level. So it'd be a good idea to revisit that and replace some of them probably now. It allows a sort of compiler independence in a sense that the code is really just basic standard code, and it calls libraries and then it calls other functions which are then compiled with MVCC. And then if you're running on CUDA, then you're guaranteed to have the MVCC working, and the MVCC would only be applied to that particular CUDA code, so the CUDA kernels. So there is no lock-in a sense this way, because they can be replaced easily. Performance libraries help tremendously. Kubla, Solver, Sparse, FFT, and whatnot. Small parts of the DFT code does have CUDA utilization as well. It's using the batched FFTs. Kublas as well and KuSolver. The NG version for multiple GPUs are also very useful for generalizations on a single node. NCCL also I've dabbled with it recently. More word on it later. Handling the memory manually is not actually that difficult. There are clear documented library calls for simply copying back and forth and whatnot. And one of the previous speakers mentioned that in ACC they were actually suffering from these memory accesses, and they had to copy manually before the launch of the ACC kernels. Or if I understood correctly, that was the idea. Well, that makes it even less of a reason to use ACC, in my view. Easy asynchronous launches, again, it's a native feature of the CUDA environment that launches are asynchronous, and most things are really asynchronous. Even the library calls, you're creating a context object, set the stream you want it to run on, and simply send it off. This way, build a sort of a graph for the device to run through. And also, not last, it's fairly trivial to couple with host threads or OpenMP threads. Something which, in my limited experience, it wasn't that trivial before. You could compile with ACC or with OpenMP, or if both of them were enabled, somehow things could be strange. Don't quote me on that maybe, but it was some difficulty I've seen with that. So there is no such problem here at all. And actually, the way I'm using multiple GPUs per process is through allocating a thread per device. Right. The high-level scheme is mentioned the same high-level Fortran CPU code. There is no checks whether it's running on GPU or any branching or if defs or any of that during most of the code, only at the very initialization step. Specific CUDA routines are being relinked in place of the CPU low-level routines. And these can be also relinked dynamically later with a check if really necessary, but in most cases it isn't. We'll come to a place where it might be useful. Dynamic dispatch is this code, I guess. So far only for CPU and NVIDIA GPUs, but with the abstractions in place, it's actually going to be fairly simple to support other devices. The bigger difficulty might actually be not the actual CUDA code itself, but the availability of other libraries to match the functionality and performance of the CUDA versions. Multiple GPUs per process are used with threads, as I mentioned. The GPU nodes do tend to have large amounts of RAM, and being able to hold the whole matrix in the main memory, then work on it over the GPUs and send the results back is useful rather than having to go across node links. Then the overhead will be much, much worse. Simple bookkeeping is with the threads can easily use OpenMP scheduling to schedule different devices working on dynamically on chunks of code. Another way of using multiple devices implemented in some of the code is also with the MG APIs. So these can handle generalizations of large matrices on a single node very efficiently indeed. So recent example from a few days ago, if I remember, a 70,000 by 70,000 matrix generalized in like 5 minutes on a one node. Prepare, very simple to use, prepare data, code solver, and we're done with it. Specific patterns, so that's maybe too technical now, and time is not our friend, so skip through, but general idea is that one can represent lots of things as series of matrix multiplications, which are simply applied. In some cases, it's more complicated, where there is slight overlap of tiles, which needs a little bit more special handling. And I'm not sure how easy would this be done in OpenACC. Maybe I should look more carefully in such examples to be convinced. In CUDA, it's actually fairly, not exactly trivial, but simple to do. Yeah, symmetrization, sparse, dense, sparse matrix products are good stuff. As the previous speaker also said, I have also, in some cases, specializations depending on the matrix size in the BSC solver. For example, whether a whole algorithm is run on GPU or CPU or on multiple GPUs. As a decompensation example, and also the construction of big matrix. This is an example of memory access for one particular object where none of these things quite applied. And the easiest and rather well-performing implementation was simply to use managed memory and do a simple CUDA code and be done with it. CUDA in the sense of actually calling the Kubernetes libraries rather than still doing by hand things. Performance lessons, again, as most other, well, everyone else said, use profiling and analysis tools. It helps. I mean, without it, you just can't really claim anything. They're fairly easy to use and help you find chunking parameters which maximize the memory transfers and computing overlap. Also, there's cases where a single kernel might try to simply use far too much resources unjustifiably and waste them. So adjusting the launch parameters this way is useful. Having some sort of heuristics to do that is great also. That's one good thing actually about ACC, that they have these things embedded in the code. You don't have to bother with it. But for manual written code, that might be useful. I'm actually thinking it might be a good option to see if a particular file can be done with ACC to gain advantage of that, compiled and then linked to the other code which shares the other libraries. Packing semi-sparse data to help vectorization also is quite helpful. More performance lessons. Sometimes it's probably one of the very few exceptions where using simply standard libraries is not the best approach. The example I have in mind is a similarity transformation with very sparse projectors and a dense matrix in between. In that case, writing a simple CUDA code without much trickery actually does the job much faster than using two products of the specialized sparse library from codes from QSparse. Pint allocations are very expensive. Using some sort of pool allocator is probably a great idea, or simply not deallocating and allocating, or removing registration and re-registering again memory too often. Peer access, that's device to device, can actually slow operations at times. If it's not needed in a particular time, good idea could be to switch it off and then switch it on before calling functions which use it. In my view, single precision also deserves a look. It is significantly faster even on the best hardware, and it's much faster than double precision because of various other reasons on consumer hardware. if it's judged that it could be a good replacement also for some algorithms, I think it's a very good idea to be used. And C++ templates can help tremendously with this managing all the complexity of having the split codes. Pitfalls. It's not all great, but there are actually rather few. Asynchronous launches are great, but they can also introduce subtle bugs which are rather tough to find. So it's crucial to have a very good test suite or some local unit test to check exactly as you're doing things, whether you're still on track. Errors are saved per device and show up much later on at some point. It's really not quite obvious, or most of the times, where they come from and why. So that's another thing one need to be careful about. Fortran, using the CUDA allocated memory forces you in a way to use pointer types. Could avoid it by registering the memory, but again, needing allocated memory in other contexts is useful. So I guess you just have to live with it. GC treats them as non-contiguous objects, even though they are, or even if they have the correct contiguous attribute. CF pointer doesn't let you easily choose a range. You'd have to have another pointer, then to relink, it's a bit of a mess. Another pitfall, I guess, not really Fortran related, but CUDA rather. There is some strange data type arguments to recent versions of CUDA libs, sort of a generic interfaces, but I think there's a better ways to do that. Operational matters, CUDA-aware MPI, as good as it is to send data directly from GPU memory, can be a bit of a pain when the interactions with the queuing system on a cluster is not quite worked out perfectly, or when they assume only a very particular use case where you just have a single process per card. In my case, you can have 2 cards or even 4 or more cards per process if really necessary. It might be possible to, MPI standard doesn't really know about the GPU, so all that happens in MPI unit. The only way to have any control of that is using some environment variables from outside to try to fiddle with it, or to specify which devices exactly are visible. And it's a bit of a mess. The multi-process service, rather inconvenient to use, though once one gets it going, it's tremendously useful for tiny cases. Things go super fast, indeed, for small systems with huge amounts of K points. Another strange thing is that vendors sometimes just link devices in weird orders. I think Jiri was somebody who mentioned that in the beginning of the day, that you might need to reorder things for optimal binding to avoid cross accesses. And the result is that there is a very noticeable difference once one tries to run on CPUs only again. Nowadays, nearly all the calculations with our codes are done on GPUs. It's just night and day difference. Productivity, example job for Chromium Trihalite, GW plus BSC, probably 15 iterations or so, if I remember. On 9 good CPU nodes, that's a 64 core EPIC high frequency on TGCC, 2 of them per node. You're looking at an overnight job, and on just 3 good nodes of Joules booster, that's a couple of hours. And you can do that sort of molybdenum sulfide or not on BSC, which is quite nice. Enables previously unreachable cases also. Is an example where one was thought from Microsoft Q, I think, was developing a quantum computer and investigating various like device, sort of micro device things. So it's a Schottky junction from indium arsenide nanowire with aluminum substrate, and that run on Joules for 4.5 hours on 288 nodes, and total performance was close to the whole of Archer 2. And the vast majority of that run, something like above 80% of the time, was spent at efficiency of above 90% on the GPUs, because self-energy making is the heaviest part. And that's also the one that's easiest to optimize. And thank you for the attention. I think I was maybe 5 minutes late. I'd like to invite you also to Quest School we're running in May, if anyone's interested. Any questions?
So thank you very much, Dimitar. Let's see if there is any question. I don't see any raised hands at the moment. I have a question. So you're probably one of the few that I'm aware of that are using the so-called MG extension of our library, the one that allows to use with one MPI drive multiple GPU, because a lot of codes, that's just reality, have been parallelized first with MPI. So the binding one MPI, one GPU is just convenient, you know.
Yeah.
But then obviously that opened up the challenge of finding, for example, a multi-node, multi-GPU type of library for doing, for example, Eigensolver. But you went to the route of having one MPI and multiple GPU. So this is a fixed constraint in the code. So even if you have 8 GPU on the node, you put one MPI and use 8 GPU, or the number of GPU you pick up per MPI, it's very much input dependent. So how
it's input dependent. So you can depend.
Okay.
If you have a small system with a huge amounts of K points, for example, you might want to use the MPA's service and pack a whole bunch of MPI processes because the parallelization on MPI and KQ points is done only on MPI. There's no multi-threading on that. The multi-threading is always in a lower level, or also the GPU works in the lower level. Yeah, you can pack like many, not that many, but reasonable enough number of MPI processes with the MPI service per device, and this will work great. You can also run a single node a single process per node. That's the other extreme. So that's only really useful if you have a large system and you want to fit everything in the host memory. You have a fat node or something like, well, Jules has this 512 gigabytes of RAM. You want to use all that, and you want to minimize as much as possible the copying of memory across nodes. Yeah. So yeah, it's input dependent.
And which extreme is more popular? Or which one is more useful to produce science?
Most popular is actually to run one process per card, or maybe one process per 2 cards, that kind of thing. In my view, the best idea is probably to run one process per InfiniBand link.
Okay.
Because this way you can easily take advantage of the networking. So if you use just one process per the whole node, then that one process, I'm not sure how easy it would be to use both cards simultaneously. If MPI library somehow internally does it, great. I'm not exactly aware of it, whether it's done. So in my view, it would be great. And then one process can, without any issue, handle, in the computational part at least, can handle more than one card. It's actually more efficient than having more process and then they share the memory with so on.
Yeah, I think it would be probably easier to do with Nickel, because Nickel allow, so before reaching out, for example, InfiniBand, Nickel leverage NVLink internal on one node to shuffle data. So he usually try to prioritize the fastest path.
Yeah.
Okay, interesting. It's definitely, I'm not saying uncommon, but it's a different use case in the way to approach the use of GPU compared to other codes. So thank you.
My experience comes from having experience with ScalaPack before, and also I've tried the CSCS library, Cosma was called, I think, for the multiplications, and it's a great library. And the good thing is it actually gives you the same performance that you get from the MG code on a single node. But once you go beyond the single node, it's a pain. It can slow down significantly.
Okay.
It's just a physical fact. There's nothing that can be done about it, really. It's what it is. The access to main memory is significantly faster than access over InfiniBand.
Yeah, makes sense.
Yeah.
Okay,
so things like generalizations, for example, these things are already suffering significantly, going from 1 card to 4 cards per node. Going beyond the one node, then you lose all sorts of efficiency.
I see.
And it was done very often in the past with ScalaPack, but it's just not an efficient way to go about it. And the idea here is that there are many computers coming up with GPUs, but that wasn't strictly the case a couple of years ago. And even now, it's not that simple for many people to find very many high-performance GPU nodes. Very many people actually have some access to departmental cluster, whatever. Maybe they got a few nodes, but there is a competition for that also on the queue. How much you're going to wait to run your thing on the GPU nodes? So being able to really to hit the maximum efficiency possible for a reasonable scale input. Once you have a large input, there is no question. You have to go to HPC. There's no.
So essentially, your main optimization function has been leverage the node, what is inside one node as much as possible.
As much as possible, and then use MPI for not that much just communication between the nodes. Yeah.
Just to go out. Okay. So thank you very much for the contribution. It was very useful.
So, yeah, we're looking now at going lower scaling, and in that mode, we will have to go beyond one mode, maybe drop K points altogether for that. But there might also be cases where you have a supercell of sorts with some K point, which allows you some flexibility on wave function beyond the supercell, but still more of a complicated solution. So for that, I'm looking at the CSS libraries and some others as well, and how far they can